We continue on in Chapter 2, which is about relational thinking. Today, our topic is sets. Informally, a set is just a collection of objects. In math, oftentimes those objects are numbers. However, they could be anything, like the set of cows in Indiana or the set of stars in the sky. Now, in this section, we'll be talking about sets. In particular, we'll be talking about what it means to be a member of a set, what it means for one set to be contained in another set. We'll also be talking about ways to take two or more given sets and form new sets from those. And then finally, we'll be talking about some identities among sets. We begin with some notation about sets. First, remember a set S is just a collection of objects. If X is an individual object, either it lives in S or it does not. If it does live in S, we say that it's a member of S, and we use this symbol to indicate set membership. So this expression that I'm underlining means that X is a member of S. Now, how about notation for sets themselves? So sometimes it's possible to list all of the members of a set. If that's the case, then you can characterize S by just listing its members inside of curly braces. Now, sometimes that's unwieldy, especially for sets that are infinite sets. And so another way to indicate that, or to characterize the members of a set, is to use defining properties of the objects in that set. So in that instance, what we do is we say that the members of our set are all of the objects possessing a certain property. On this slide, we have a list of some common sets of numbers. The first set is the empty set. It's denoted by a circle with slash through it, and it is the set that has no members. Now, you might be wondering how in the world that could possibly be useful. Well, we'll have to see in the future how we might use this empty set. Okay, the natural numbers are denoted by n, and this is just the set of counting numbers beginning with 1. So it's 1, 2, 3, etc. And notice here we're using our set notation where we're listing the elements of the set in between curly braces. So the whole numbers are denoted by W, and they are almost like the natural numbers, except we also include 0. Okay, the integers are denoted by Z. These are the whole numbers and their negatives. Okay. Now, the rational numbers, you might remember that this is the collection of fractions. And now, for the first time, we're going to use our set notation that uses the notion of a property to characterize the elements of a set. So Q, the set of rational numbers, is the set of all fractions, A over B. So that's the objects. And now to the right of this vertical slash, we're going to put the properties that must be satisfied by these objects. So we want A and B to be integers. And we want B, the denominator, to be non-zero. So that defines the entire collection of rational numbers. So the real numbers are denoted by R. So remember, that's our continuum, our number line, consisting not only of the rational numbers, but also of other numbers like pi and e and the square root of 2 and things like that. And then finally, we have this set of complex numbers denoted by C. This is the set of all things of the form a plus bi, where I squared is equal to minus 1. And a and b are real numbers. There's also the important notion of set containment. So this symbol, or this expression here, means that for all x, if x is a member of A, then x is a member of B. So that's illustrated graphically here, right? So if x is in A, then it must also sit within B. So for example, using the sets that we talked about on the previous slide, any natural number is also an integer. Any integer is also a rational number, and any rational number is also a real number. So here we get some practice in verifying set containment. So here we let E denote the set of even integers, S will denote the set of odd integers, and then we have this set X, where if you parse this set notation, it's telling us that X is the set of all integers that have the property that they are the sum of two odd integers. So we want to show that this X is a subset of E, the even integers. Okay, well, how do we do that? So every subset proof begins essentially the same way. So I need to start with an arbitrary member of X. So we're going to let A be an X. And then what I need to do is produce an argument that culminates somewhere down at the bottom here, where I'm able to conclude that A is a member of E. If I can do that, I will have shown that every member of X is a member of E, and therefore that X is a subset of E. Okay, so since A is a member of X, I can write A as, little x plus little y. Where little x and little y are members of S. Now, x and y are, S is the set of odd numbers, so little x and little y can be written as multiples of 2 plus 1. So that's for some integers. M and N. We have that A is x plus y. But x is 2m plus 1. And y is 2n plus 1. And once the dust settles on that calculation, what you get is that's 2 times m plus n plus 1. So since A is a multiple of 2, we know that A is even. And so we can conclude that A is a member of E. Okay, so I want to point out here that how the proof began and how the proof ended. So we want to show that X is a subset of E. To do that, we began with an arbitrary element A in X. We did some stuff. And then we concluded that A was an element of E. Every subset proof looks more or less like this. There are a number of ways we can take two or more existing sets and form new sets. Two of those ways are shown on this slide. So the first is this notion of set union, right? So it's denoted by A with the cup symbol B, and it's the set of objects that are either in A or in B. So this definition right here says it's the set of objects that are either in A or in B. So you can look down here at this Venn diagram. So the shading indicates all of the elements of A union B. So another thing we can do with two sets is look at their intersection. So that's denoted by this cap symbol. And it is the set of all objects that are in A and are in B. Okay, so down below we see a Venn diagram, and the shaded area you see is the intersection of A and B. It's all the stuff that lies in A and in B. So another thing we can do to form a new set from an existing set is to take the complement. So to do that, what we have to have is an agreed upon universal set U in which our set A lives. So to form the complement, all we do is we look at all of the elements of U that are outside of A. In other words, all the elements of U that do not live in A. Elements of U that do not live in A. So the shaded region in the diagram is the complement of A, and that's denoted by this prime symbol. So we can also take the Cartesian product of two sets, so that's indicated by A times B. And what we're doing there is we're looking at the set of all ordered pairs of objects where the first object is an object from the set capital A, and the second object is an object from the set capital B. Now this notation is rather leading. It's sort of reminiscent of multiplication, and indeed, if A and B are finite sets, if you count the number of objects in the Cartesian product, A cross B, the number of objects there is the number of objects in A times the number of objects in B. So another way to form a new set is to form what's called this power set. So the power set is just the set of all subsets of X. And here we need to remember to include, always include, the empty set. Remember we talked about the empty set a while back. So the empty set is a subset of every set and the set itself. Okay, so when you're forming the power set, remember to include both the empty set and the set itself. here we get a little bit of practice forming new sets from old. In this example, A is this finite set 1, 2, 3, 4, 5. B consists of 4, 5, 6, 7, and 8. And both A and B are going to be living within a universal set U, consisting of the numbers 1 through 10. All right, so the first thing that we're forming is this A union B. So that is all of the objects that are either in A or in B. So 1, 2, 3, 4, 5 are in A, so they're automatically going to be in A union B. And then I throw on the remaining objects in B. Now, one thing you might notice is that 5 occurs in both A and B. In fact, 4 does too, right? And so you might be wondering, when we form the union, do we need to list 4 and 5 twice? And the answer is no. So you only list 4 and 5 once. Okay, the next object is the intersection of A and B. So intersection, remember, is all of the objects that live in A and live in B. And notice that the circled numbers here are exactly the numbers that occur in both A and B. And so that is our intersection. And then we form the complement of B. Remember, that's all of the things in the universal set that are not in B. So I'm looking at all the numbers 1 through 10 that are not in B, and these indeed are all of those numbers that are not in B. Okay, next we're forming a Cartesian product. So this is going to be a set of pairs where the first number in each pair is going to come from A intersect B, and the second number in each pair is going to come from A. So A intersect B, remember, consists of the numbers 4 and 5. So when I look at all of these ordered pairs, the first entry will either be a 4 or it will be a 5. And indeed, that's what happens, right? Because those are the elements of A intersect B. Now for the second entry in each pair, I want to draw from elements of A, which are the numbers 1 through 5. And I see, indeed, I get a 4, 1, 4, 2, 4, 3, 4, 4, 4, 5. So those second entries have exhausted all the elements of A. And then I go to the first element being 5, and I again exhaust all of the elements of A in the second entry. Okay, and sure enough, if you want to check to make sure that you've gotten everything, the expected size of this Cartesian product should be the size of A intersect B, which is 2, times the size of A, which is 5. And so the size of the Cartesian product should be 10. And indeed, if you count all of the ordered pairs, you should find 10 ordered pairs there. Okay, finally we have the power set of A intersect B. So we're going to list all of the subsets of A intersect B. Now remember, we should start, if we start from smallest subsets to biggest subsets, the very smallest one is the empty set, so we can't forget it. Then we list the subsets of size 1, namely 4 and 5. Now remember, you might be wondering, why are we putting these braces around the 4 and around the 5? Here we are regarding those singletons as not being merely elements of A intersect B, but rather as being sets themselves, right? So that's why the braces are there. And then we can't forget the set A intersect B itself as being a subset. So there we have the power set. On this slide, we have De Morgan's laws for set equality. And before we can talk about those laws, we need to know what it means for two sets to be equal. So set S equals set T. That means that each is a subset of the other. So that means S is a subset of T, and T is a subset of S. So if I'm going to verify that two sets are equal, so if I'm going to verify a statement like this, then I need to do two things. I need to show the first set is a subset of the second, and then I need to show the second is a subset of the first. So anyway, now down to De Morgan's laws. De Morgan's laws say that if I take the complement of a union, then that is the intersection of the individual complements. And also, the complement of an intersection is the union of the individual complements. We're going to prove the first of De Morgan's laws. And remember, that's the one that says that if you take the complement of the union, then that's the same as the intersection of the individual complements. To show two sets are equal, we need to show that each is a subset of the other. So we'll begin by showing that the complement of the union is contained in the intersection of the individual complements. Now, to show something is a subset of something else, we need to start with an arbitrary element of the first set. So we're going to let X be in this complement of the union. So let's unravel what that means. That means that X is not a member of A union B. Therefore, it's not true that X is a member of A or X is a member of B. Now, if we look at this formulation, we're saying that it's not true that something happens or something else happens. Now, that formulation should remind you of De Morgan's law from symbolic logic back in chapter 1. And if we apply that De Morgan's law to this situation, what that says is that X is not in A and X is not in B. So that allows us to conclude that X is in the intersection of the individual complements. Right, remember A prime is is the stuff that's not in A. B prime is the stuff that's not in B. All right, so we have done what we set out to do. We started with an arbitrary element in the first set, and we made an argument that it must also be an element of the second set. So now we need to do the opposite thing, right? We need to show that A complement intersect B complement is contained in the complement of the union. And here, more or less, we're able just to reverse, in this particular case, we're able to reverse the argument that we just made, right? So we're going to let X be in the first set. So we let X be in A complement, intersect B complement. Then we unravel what that means. That means that X is not in A. And X is not in B. So it's not true that X is in A or X is in B. So X is in the complement of A union B. And again, what have we done to show the subset relation? We took an arbitrary element of the first set. We made an argument and showed that that arbitrary element lives in the second set. And now we're done, right? We've shown that first of De Morgan's laws for sets. So we finish with a discussion of a set identity called the inclusion-exclusion principle. And it has to do with counting elements in the union of two sets. So first of all, some notation. If you want to denote the size of a set, you use vertical bars. So if S is a set and you put vertical bars around it, that's the number of elements in the set S. Okay, now on to the counting problem. Let's suppose I've got two sets. Let's suppose we've got a set A here, and I've got a set B here. And suppose I want to count the objects in the union of those two sets. So the natural thing to do, maybe, would be to first take the set A and count everything in A. So we count all those objects in A. And then I turn my attention to B and I count all of the objects in B. And I put those two counts together, but then I realize that in this central area, that is, in this intersection, I have counted those objects twice. And so instead of merely adding the number of elements of A to the number of elements of B, what I should do is subtract off the size of the intersection, because if I don't do that, I will have double counted the intersection. So this formula that results is called the inclusion-exclusion principle. And here we have an example of using that. So we've got the Master of the Universe Society at a certain college accepts members who have perfect SAT scores or 4.0 GPAs in high school. Right, so you can, so of the 11 members of the society, 8 had these perfect SAT scores, and 5 had 4.0 GPAs. The question is, how many members had both perfect SAT scores and 4.0 GPAs? So we're told in this inclusion-exclusion equation that the number on the left, that is the size of the union, is 11. We've got 11 students that have one thing happening or the other. And then we're told that 8 of those students live in set A, which is sort of the perfect SAT land. And then we've got 5 students who live in set B, which is the 4.0 GPA land. And the question is, how many members are in the intersection? That is, how many people had both? And we have 11 equals 8 plus 5 minus the size of the intersection. So that forces the size of the intersection to be equal to 2. So we conclude there are 2 students who had both perfect SATs and 4.0 GPAs.